So I think we can now get started. I'm going to share my screen. So good morning, everybody again. Welcome to the 22nd CONGA meeting series. This is a meeting that we gather to educate ourselves, get some information, learn about techniques, development of ground-based instrumentation, some science, results. So I'm going to talk more about that shortly. But before we get started, I'm excited to announce to you today that we have a special guest that will be talking to us. Will be presenting their work today, Dr. Daniel Okoh, and um, they'll be he will be talking about let me see, this is disturbing me here. Let's see if I can move it. Okay, so he'll be talking about the work titled integrating space and ground-based TEC observation and operational machine learning uh, calibration framework. So Dr. Okoh will be introduced shortly by Yenka. Yenka is here with us. Is one of the leadership in this CONGA meet. She's here always, and she has been supporting this workshop and everything that we do here. Yenka has been giving us full support from ICTP, and she will be introducing our guest speaker for today. But before we get to that, I want to mention a few points that we normally go through before we get our meeting online, in progress. So um, if you are new here, this is the time we want to welcome you. If you are attending this meeting for the first time, um, let me see if I can actually see if we have some people that are attending for the first time here. We have somebody from Burkina Faso. That is fantastic. Are you attending for the first time? Can you please introduce yourself very quickly? And we're going to do that very, very quickly, okay? I promise. So if you want to introduce yourself, we want to get to know you. We want to be able to work with you in the future. When we have our instrument, we want to send it out. We want to know you. So this meeting allow us to do that. So if you want to introduce yourself very quickly. Anybody? Okay, so I know
Please,
we
are
have
you to introduce everybody or a new persons?
just the new people. If you are new because of our time,
Okay, thank you.
because I don't know how much Dr. Daniel is going to use on this program. He has like 30 to 45 minutes, so I want to make sure we maximize our time. So if you are new, attending this meeting for the first time, so you can just introduce yourself. And I already know you, Dr. Francis, so don't worry. We have you here. You are our prominent attendance of this meeting. So
Thank you.
yes, no problem at all. We want to know other people as well. So please introduce yourself. We can quickly take 5 minutes to do that. Okay.
Okay, good afternoon, everybody.
Good afternoon.
I'm Zundi Christian from Burkina Faso. It's the first time we follow your program.
Yes, that's
It's
good. Nice to meet you.
nice to know your program. Mr. Frédéric Pitou from France
Oh,
gave us
okay.
the link to follow your presentation.
Okay. Good,
Yes.
good to know. Good to know that. And if you could complete the form, do you complete the form online for the membership for CONGA?
And no.
Okay, so I'm going to send you that link so that we can have your email and send you updates and other information. Okay?
Thank you very much.
Yes, I will put
A pleasure.
I'll put the link on the in the chat in a moment so that when you see that you can click on it and get registered to be a member of this meeting. And we will be able to send you other materials. So, any other person that wants to introduce themselves?
Ibrahim?
I think we have a lot of people from Burkina Faso today. So,
Uh,
all right.
yes. Uh, a student, Ibrahim Traore, must be looking the program. I don't
Okay.
see him.
Okay.
Ibrahim, tu es là?
Oui, exactement. Oui, oui, je suis là. Je m'étais déjà présenté avant que vous ne soyez en ligne.
Ah, d'accord, ok.
Et voilà.
Ibrahim already presented himself in
Oui.
the
Okay. Thank,
very early of the early hours of the meeting.
thank you
So
very much.
yeah, I already introduced him. So that's why I said we have a lot of Burkina Faso
Burkina Faso.
group here today. Ghana used to win the race here. The meeting, they are always this meeting is always very much attended with Ghanaians and Nigerians. Now we have Burkina Fasos. We used to have Ethiopians as well. So it's always a full house here with different countries. And this is getting more exciting because we have all of the countries that we need to distribute this instrument when when we get ready. So this is really good. I'm going to share my screen now and continue with the meeting just to mention that we have a new website. I'm going to also put that link in the chat. This is the link to the website right now. So most of the updates, we put most of our updates on the website as well. So feel free to visit the website at any time. And also, if you want to give a presentation of your work, um, you can just email me this presentation and we will take it up from there. We will contact you to get more information about it and send you all the things that you need to know about our meeting. So if you have some instrumentation or you are in charge or a director of any instrumentation or you have some beautiful or interesting scientific results that you want to share, so this meeting allows you to do that. It's a form of education. This is what we call educational outreach. This is the aspect that we call educational outreach. So feel free to share your work here. And just to continue this meeting, I want to also mention that this meeting is um, we are here to build a network of people that can work together, right? So we are here to get to know. That is why the introduction part is very important, where we get to know you and we can work with you in the future. We also do training and development of our members in terms of ground-based instrumentation. And this morning, we have the privilege to have very renowned scientists here to also discuss what they are doing in their work at the Nigeria Space Agency. So that is very key part of what we do here. And there are so many things that goes on with data nowadays. So CONGA is trying to establish a situation where we have free accessibility to scientific data. So all these data, all these locations that you see on the map are where CONGA will be putting instruments. The CONGA instruments will be located around these stations. So this is key to our initiative. This is what stand CONGA out of other agencies. So we have recognized or allocated different locations in the equatorial region of Africa where there are gaps in scientific data, ground-based data that we could leverage and put some of these autonomous instruments around this region, and we can study more scientific, we can have more scientific understanding of what is going on, a complete knowledge of ionospheric science. So this is part of our mission. And the good news is that we have this proposal in a top place right now. We are collaborating with the University of Massachusetts Lowell to write the proposal for this instrument, which is the best news that I have for you today. So in the next 6 months, we should get this proposal submitted. So CONGA is moving forward, and in the coming years, we should have not just this map, but instruments across this region. You understand? So with that, I will continue my announcement after, if we have time after the talk. But I will leave the floor for Madam Yinka to introduce our guests for today so that we can get started. Yinka.
Okay, thank you, Olu. Hello, everybody. So it is my pleasure to introduce Daniel. Actually, it's the second time in the year that I have the pleasure to introduce Daniel. And the first one was last month in Costa Rica. Remember, Daniel? Okay, so Dr. Daniel Okoh is a researcher specializing in ionospheric physics, GNSS applications, and space weather modeling. He works on data-driven and physics-informed approaches for modeling ionospheric parameters using satellite and ground-based observation. He is the principal developer of AfriTech, the ionospheric African model for Africa, and has contributed to machine learning frameworks for operational ionospheric calibration and prediction, with a focus on strengthening ionospheric monitoring capabilities in Africa. So Daniel, over to you. You can share your screen.
Okay, thank you so much, Yeka. Nice to meet you again.
Yeah.
Okay, so I'm sharing my screen. Okay. Yeah. So am I sharing now?
Yes, it's you are sharing, and if you can make it full screen.
In slide. Okay, yeah.
Yes.
That is what I just did.
Okay, so I think it's still processing. We are seeing we are still seeing part of the screen, maybe. Yeah, probably it's still processing.
Oh,
Yes, there you
okay.
go. There you go.
Okay. Yeah, thank you.
Yeah.
Okay, so I thank the team, the CONGA team, for the nice work they are doing, especially Dr. Jonah and the team. So very quickly and briefly, I'm going to talk about one of our recent projects that is about integrating space and ground-based tech observations. So I will be talking about it shortly. I did this work with a number of persons. Some of them are also here, including Yenka and Bruno, who are here. Okay, so in the course of the talk, I need to minimize this. Okay, so I will be giving a quick introduction, then talk about the data and the methods we've used, and then the results and discussions. So since I will not be able to touch everything about this work in these few minutes, I normally put this first slide so that anyone that is interested in more details can always get details from here, from the paper. So the paper is available online and they're at the link I pasted here. Okay, so starting with the background and the motivation, I will quickly just say that the essence of the work is to kind of be able to integrate space-based observations into what we would have had if we had ground-based observations. And this is also in line with the dream of CONGA to install or to distribute network of equipment across the African region. So in the course of developing the AfriTech, which led to this work spatially, is that we realized there were some huge or vast region that really lacked ionospheric measuring equipment, especially across the Sahara Desert. And this was what led to the thought of also being able to incorporate space-based measurements from satellites. So I start by talking about TEC, which I presume most of us already know. So it's the short for total electron content, and it's in physics, or in terms of physics, it is the number of electrons. So if this on the right we have the Earth, and then surrounding the atmosphere, or essentially the ionosphere which we're interested in, the total electron content is the number of electrons we would find in that cylinder that has a cross-section of 1 meter squared if we passed it through the entire region of the ionosphere. So the number of electrons we would find in that cylinder is what we call the total electron content. And one TEC unit is 10 to the power 16 electrons per meter squared. So the question is, why is it important to study TEC, or why is TEC important? So it's important usually to improve GNSS positioning accuracy. We need TEC, essentially, it indicates or it tells us how much delay a radio signal, especially from GNSS, what they suffer when they pass through the ionosphere. So the delay they experience is what is proportional to the TEC, so it's indicative of the TEC. So it's a proxy that we use for studying and monitoring the ionosphere and space weather. Okay, so the problem, like I explained, is that we normally can measure TEC from ground-based GNSS receivers, like the ones CONGA is planning to install. There are a number of them, relatively few in the continent, across the continent. And yeah, so these receivers, they continually record measurements over time at given Earth locations. So wherever we install them, we could continually measure, record, observe the ionosphere at those locations. But we can also quite recently be able to measure or study the ionosphere using satellites, especially measuring properties through radio occultation techniques. And in this case, since the satellites are in motion and occultations happen at different places, and yeah, so we usually will not get measurements continually over a given Earth location, but at least the measurements are distributed across the globe, or at least over the equatorial region in the case of the Cosmic 2, which I will also be talking about. So yeah, the problem is that we could directly get these measurements from Cosmic, from satellites. Yeah, but the second problem that it poses is that the the calibrations are different. So for example, when we have a ground-based GNSS receiver, we're able to integrate TEC up to above 20,000 kilometers, which is the altitude of the satellites. But when we get radio occultation measurements from cosmic, especially then, we are usually able to integrate only up to about 500 or 800 kilometers. So it's about 500 for Cosmic 2 and around 800 for Cosmic 1. So the problem here is that these satellite measurements normally exclude plasmaspheric contribution. So the TEC that is contributed by the plasmasphere, which is above thousands of kilometers, are not included in what we in what the cosmic satellites, what they measure. So just on the picture showing that the GNSS, the ground-based ones are able to see through the entire medium that way. But when we look at the cosmic data, we're only seeing at up to part of the ionosphere. Although this part of the ionosphere is where we find most of the electron concentration, but still a part of it, a part of that electron concentration is missing in what we get from the cosmic. Yeah, so that is the objective of the work. And what we essentially want to do is to recalibrate now this cosmic TEC so that the match, we get what is equivalent to what we expect from a ground-based GNSS receiver. Okay, so specifically, we developed two models in this work, which we call ROTEC A and ROTEC B. So ROTEC A is like the quick thing we did mainly for and also to support operations. Then ROTEC B is kind of research enhanced. And then so it includes more parameters, but also makes it a little more difficult for operations because more parameters means we need those parameters to be able to calibrate the TEC. So we'll see what they are. So the output is, and what we expect eventually is that we'll be able to output in near real time a corresponding measurements from the cosmic system. So coming to the data we used data from Cosmic 1 and 2, as I've already mentioned. So the Cosmic 1 mission was the earlier mission of Cosmic, and it was launched in 2006, and it went up to 2020 was the last time we had data from it. While Cosmic 2, which is like a replacement, was launched in 2019, and it's still operational. But for this work, we had used data from 2019 up to 2025. And the products we used are electron density profiles, HMF2, F0F2, and cosmic TEC measurements from those products. They are in cosmic terminology. They are called the level 2 ion PRF products, which are obtainable from these websites. So anyone can go here, download the data, the raw cosmic data in this format. Then coming to the GNSS TEC, we used data from about 1,260 IGS stations, and specifically we utilized the ICTP GNSS TEC service. That is the one that Yenka and Bruno work on at the ICTP. So there's basically their software that does calibrate data from the IGS stations. And we directly obtained already calibrated GNSS TEC from these stations. So we obtained virtually all data that is available there, and then average them. It comes in 30 seconds, mainly 30-second resolution. So we average them to 15 minutes in order to match or collocate the cosmic data. So just showing sample distribution of what these measurements or what the stations look like. So the blue dots are the GNSS stations. from the 1,260 stations that I mentioned in the previous slide. And then the green dots are data locations for Cosmic 1, specifically just only for 1st January of 2007. So this is just for illustration. And for Cosmic 2 are the red dots, which is specifically for January 1st, 2020. So it's just what we see is that the cosmic observations are well distributed across the globe. Unlike the GNSS measurements, we can see a lot empty spaces in the African continent, which is part of the problem that CONGA is also addressing. Okay, so just talking about distribution of the entire data set according to year, that is what we see on the right-hand side on the bar plot. So data from nearly every year is represented. And we did some kind of co-location. So the first thing we did was to co-locate GNSS and cosmic observations. So wherever we have a GNSS station, we only take cosmic measurements that come within 5 degrees of that station. So we map any observation that comes 5 degrees of that location of the GNSS station to that particular station. And also they used a temporal criterion of plus or minus 7.5 minutes, because remember we averaged the GNSS data in 15 minutes, so we could do plus or minus 7.5 minutes of any cosmic observation to co-locate any given GNSS profile. We had over 3.5 million good quality paired data sets. That's after we had paired cosmic and GNSS data. And then at least we had more than 20,000 for any of the years, as we see on the right-hand side of the plot. Okay, so one of the first things we did was input feature engineering to find how significant the inputs we decided to use are. So, and we did this using the idea of random forest, and the parameters, the input parameters we explored are the ones listed at the bottom of this bar chart. And then the results show kind of normalized feature importance that we get from the procedure. So the procedure essentially showed, as we expected, that the cosmic TEC was the most significant parameter we needed to estimate the GNSS TEC. So what we're estimating here is the GNSS TEC, and the cosmic TEC is most significant parameter to estimate it, followed by the F0, F2, also from the cosmic. So these are all virtually cosmic parameters from the cosmic profile. So the latitude of the GNSS station and that of the cosmic station, and so on. So we see that as we expected, the cosmic TEC was the most significant of them all, resulting from that procedure. Okay, so coming to the inputs that we use, which are similar to what was illustrated in the previous slide. Yeah, this is a structure of, and then the output layer, which is the GNSS TEC that we are predicting. So it's included the day of the year and the local time. So the day of the year is expressed, the day of the year cosine and sine components are expressed as shown below. The reason for doing this normally in modeling generally is to kind of create a smooth continuity between where would have like a big jump. For example, we're looking at the day of the year, which typically runs from 1 to 365 or 366, as the case may be. And after the 366, for example, we jump back to day 1. So the next day after the 366 is day 1. between 366 and 1 is a large jump numerically. So what's doing, finding the cosine and the sine component is to like bridge or smoothen that gap. So reduce that gap so that when we take the cosine and the sine of say 360 and 1, then 365 and 1, then especially after we have normalized it by dividing by 365.25 or 24 for local time, then we find that the values between the last day of the year and the first day of the next year are numerically similar, unlike using the raw values, which are 1 and then jump to like 360 and then jump to 1. Okay, so the algorithm we use for the training is the Bayesian regularization. It's just the algorithm that helps optimization, because neural networks are all about optimization. So the algorithm that helps us to get the optimized parameters is the one we call the Bayesian regularization. And then we did TANSIG activation, which I'm going to explain shortly, maybe in the next slide. So each layer has nodes, as we can see. So we have 3 layers: the input, hidden, and output layer. So the neurons in each of the layer, or the nodes or the neurons, that's what we call like these parameters. Essentially what they do is to receive the inputs, they multiply by some weights, which we're also going to talk next, and then they pass the result through an activation function, which is this same one I mentioned earlier. So talking now about the activation function, or generally what actually happens in the neural network process, is what is represented by these 2 equations. So the first equation shows how the inputs are translated into the input neurons are translated into the hidden neurons. So it's just like moving the parameters from the input layer to the hidden layer. So that's the role of equation 1, the first equation. Why the second equation moves translates what we have in the hidden layer to the output layer. What we have here is a simple case, especially if we look at the first equation and inside the bracket. So if we look at the bracket, we see that basically what we're doing is similar to the simplified line, which is like y equals mx plus c. Here is where we are trying to fit a relationship between x and y. And we know m is the slope and c is the intercept of that line. This is for line. So when we come to neural networks, the terminology, it's a similar thing, but the terminology changes a little. So we have the hidden layer now, the HM is like our output, like that is Y in this case. And then the IM is like the input. So the input IM is X, and then IWM are the weight matrices, and the B1 are the bias vector. So the weight matrices and the bias vector are 2 parameters on this equation that are like, they are like what we want to optimize. They are like what the neural network wants to get out of the system finally. And yeah, so normally we start, the process usually starts with a random initialization of the weights and the bias vectors, and then the regularization process tries to lead or to modify those weights and bias vectors to lead them to the optimal values that show the best connection between the inputs and the outputs. We have the Calibration function, and then outside the bracket, we now pass the hyperbolic tangent function, which could also be several other functions, as what we now call the activation function. So that is what I meant by the TANSIG activation. And the whole idea is that this function helps the network to learn. It's the hyperbolic tangent function we choose that is not linear that helps to learn. It helps the neural network to learn that non-linearity. Okay, so what we did in process is to try to test the hidden neurons because, yeah, we can know how many inputs we want. So we know the number of neurons in the input layer, but knowing the number of neurons in the hidden layer can be challenging, and it's a problem of trying to also, it's one of the optimization techniques to find an optimal number of neurons that do best or better represent the system we try. So what we did was to try numbers from 1 to 30, and then we tested each time with 15% of randomly selected data that was not part of the training data. And we compute the error, like a kind of averaging of the error using the RMSE that is computed in that way. Okay. Yeah, so the data also was huge. We also decided to innovate by splitting the data set into three. So the remaining 85% of the data we had after taking away 15% of the test of the data for testing, we split into three sub data sets. And then we used each sub data set to train a different model. So we also had 3 sub models, 1 to 3. And then, so what happens at the end of the day is that for us to make a prediction from the model, we have to make some prediction from each of the 3 models and then do an averaging of what it is from the 3 models. Okay, so that was for ROTEC A, the basic version of our model. Then when we come to ROTEC B, which is like the research enhanced model, we included the F10.7 as an input and also geomagnetic indices as inputs, just in case the relationship between especially the cosmic TEC and the GNSS TEC, if it changes with solar and geomagnetic activity. So this brought the total used in ROTEC A. And then, yeah, so for ROTEC B, okay, I forgot to mention in ROTEC A, eventually we decided from the performance of the models that the best networks had 26, 29, and 30 hidden. That's the number of neurons in their hidden layers, 26, 29, and 30. And when we did same for ROTEC B, we took 27, 28, and 30 as this plot shows a summary of that, of the whole results. So the green ones are ROTEC A, while the blue circles, empty circles, are ROTEC B values. So we see basically the ROTEC B values have, this is not significant. So from the results we see on the right-hand side, we see that ROTEC A error for the best systems, we got an average of about 5.5 TEC units, while for ROTEC B it was 5.37 TEC units. So the improvement was this, which we tested to see if it was significant, and we found it was not statistically significant at 95% confidence level, because we found we got the p-value to be 0.9136. Yeah, so what the results here just show is that the operational model works quite well without necessity for the research enhanced version. And since we've made it available at this site. There's another site where anyone could download the models, the networks trained from there. They are right now neural MATLAB functions. Yeah, so they are MATLAB functions or networks, MATLAB networks, which but what we have eventually want to do in the next few months is to put this like build a system that someone runs and you just decide I want to have calibrated cosmic data from this period to this period, automatically the cosmic data from the sites and calibrate it and yield the values in TEC units that should match or correspond to ground-based GNSS receiver values. So everyone can also make use of it. So just more results. We're showing the results from the submodels. So just showing the performance or kind of illustrating that the final model is actually a bit enhanced compared to if we decided to use any of the submodels. So the results here show distribution observations. We have that is actually the error distribution where we have actual TEC minus the predicted TEC. So in all cases, we see that there's a Gaussian type of distribution of the error, which is good, and it's around zero for most cases. Is a bit taller at the middle, which means that it's a bit slimmer also, which means we got more of the errors around zero for them. And then if we look at the root mean squared errors, so we see it's also the least when we compare to each of the three submodels and the correlation coefficients between the observations and looking at the individual submodels. Okay, so here also we looking at
So Daniel, I think your network is getting a little bit.
where we what we just have the cosmic like we see. So let me see if I switch.
Maybe you can turn off the video. Maybe that will help, at least for now.
Okay, share again.
Hello?
Yes, can you hear me now?
Yes.
Okay.
I think your screen is coming up yet. It's not, it went blank. Maybe you want to stop sharing and share again.
Okay. When it's up, please let me.
Okay, now,
Okay.
okay. Oh, okay. You can share again
Oh,
now.
I stopped already.
Yeah.
Okay. Okay.
I will let you know when it's up.
Is it up? Okay.
Yeah, it's up now.
Okay. Yeah. So I was showing the results of the uncalibrated
Audio is cutting. I can't hear.
on the first column here. That's the red dots. The results the cosmic, so the cosmic values. Sorry, I didn't hear you clearly.
Yeah, don't worry. There is nothing you can do about it. So just keep going. Don't worry about it. Just keep your presentation. We'll try and manage to hear.
Okay.
Yeah. I think it's getting worse. Hmm. Hello? Yeah. Hello? Daniel? I think
I think he left.
he's coming back. I think the network is giving some challenge there. And I was really enjoying the presentation.
Yeah, me too.
So let's
Wow.
see if we can come back.
A lot of questions.
Yeah. Yeah. And we have to stop this meeting at the top of the hour. Yeah, because I have another meeting. Yeah, it's back now. Doctor, are
Okay.
you back? I think the
Yes.
network was just up and down.
Yeah.
Um, we want you to share your screen, and we have like
Okay.
around 15 minutes to go so that we can entertain some questions.
Okay. I
Yeah,
will do that
10,
right
15
away.
minutes will be okay.
Yeah. Okay. I'm resharing now.
Okay. Yes.
Okay. 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 Is it better now?
Much better. Thank you.
Okay, thank you. Yeah, so I was explaining that the observations in the first column are the uncalibrated cosmic observations. So those are the raw cosmic values that are not calibrated. While the blue ones are when we calibrate using ROTEC A, and the green ones are that's the last column, when we calibrate using ROTEC B. Okay, so what we see from the first column is just definite underestimation of the cosmic uh, TEC. So as expected, we find that the cosmic values are usually lower than the GNSS values. And that is what we see by having most of the points above this line. This line is a line of equality where they are equal. And then the same thing when we do the histogram, we find that the values are distributed to the positive side of the zero, which shows that it still shows that the cosmic values are typically lower than the GNSS values. And when we look at the calibrated ones, that is the blue and the green ones, we find that they are more aligned around the line of equality. And then the distribution is also around zero and centered around zero, which shows that the technique reasonably calibrates the cosmic observations. And then when we plot this kind of averaged profiles for different parts of the day, night time, morning time, afternoon, and evening. So the night time is from 0 to 6 local time, and the morning time is 6 to 12 local time. So just these 4 parts of the day. We find also the similar behavior. The red plots, which is the uncalibrated cosmic, the errors are higher than the blue and the green ones, where in which it is calibrated. So the errors are significantly reduced when calibration is applied. And similar result is shown by this bash plot. So here we are kind of splitting or binding the observations in different categories according to local time, according to seasons, and according to the latitudes where they are in latitude. And we find, yeah, the red bars are the cosmic tech, and then the blue and the green one are where we have the calibrated one. So we see that the blue and the green bars are usually always less than the red bars, which also shows that the calibration procedure reduced the difference in between both between the cosmic and GNSS values. So in conclusion, yeah, like I mentioned, we've put the final model here for anyone at this point that has MATLAB or that uses MATLAB would be able to download the function that they supply the inputs, looking like they basically have to download the cosmic themselves. But as I mentioned, over the next few months, we want to perfect a system that we just have to decide for which period we need the data and then be able to download and calibrate the data automatically. Yeah, and we found, yeah, it's eliminated systematic underestimation and reduced the errors by about 50 to 75%. And this reduction is stable across whether we look at latitudes, local time, and seasons. The work is that we could use it for near real-time GNSS equivalent tech calibration projects that we might be interested in, like oceans or deserts where we don't have GNSS receivers. Thank you.
Thank you very much, Dr. Okoh. This is really fantastic. We have some audible challenges, but yeah, overall,
Yeah.
we
Sorry about
try
that.
to grab some of the things perfectly. So thank you very much for this wonderful presentation. And yeah, I will open the floor for questions.
Thank you.
Yeah, let's have questions. I have some questions, but we have limited time, so I'll throw it to the house. If you have any question, now it's time to ask Dr. Okoh questions about the work. If you, yeah, go ahead,
Can I
please.
ask?
Yeah, please.
Yeah, okay. Giorgio speaking here. Thank you for your presentations. I will certainly will read this paper because it's very interesting. But the case of using data from cosmic satellite, we have integrated TEC between around 500 kilometers and the GNSS satellite height. So I think the main reason why we have this huge difference with the GNSS TEC is because we are not considering the bottom side electron density to this TEC. So I think some way you are calibrating these cosmic values to maybe consider the bottom side electron density too. So is there a way to the same using the same technique, using the same methodology, to try to get only to remove the bottom side, I mean the data over the influence of the electron density profile over the cosmic satellite height, and get the TC only from the bottom side ionosphere. Is it possible for using your neural network? Yeah, neural network approach.
Thank you. I think I understand what you're asking. So first of all, looking at, maybe just to explain clearly, the cosmic, so both cosmic and GNSS, they both include the bottom side already. Only that the GNSS, yeah, includes the bottom side up to very high altitudes, around 20,000 kilometers, while the cosmic includes the bottom side only up to around 500, 800 kilometers. So mainly what is missing in the two different data sets and what makes them different is that the cosmic does not include the top side. So it's only the top side that is missing. And maybe if I understand what you are trying to say is now that the difference between the two is actually estimating the top side value. Like if we, after we calibrate and we subtract from the uncalibrated, the uncalibrated, then the difference tells us what the top side is like. And we agreed to that. And it's one of the things we think.
Okay. This is, so
Yeah.
this is not the GNSS to, I mean, this is the radio occultation TC, right?
Yes, yes,
Okay,
yes. It's
okay,
radio.
okay.
Okay, oh, yeah. It's not
Okay.
the, yeah.
It's
It's
not
not
the
the GNSS.
satellite to GNSS TC.
No,
Yeah, yeah.
I think, Giorgio, I think if I'm right, Daniel, is what you are trying to do is take the measurement from the radio occultation because,
Yes,
and you are looking at, okay, this GNSS receiver could give us plasma sphere plasmas, but
yes,
radio occultation will not be able to do that. So you wanted to
exactly.
see how you can predict the GNSS receiver from combinations of inputs from the radio occultation, right?
Mhm.
Exactly, exactly.
So,
Yes, so now I also understand the question he was asking because the
Mhm.
Cosmic also does have an onboard GNSS receiver that measures what we call the pod tech, that is the tech above the, so from the altitude above to the GNSS satellite. So that value is essentially the
Mhm.
top side, yeah, the top side component of the electron content. So, but that
Yeah.
is not what we used. What we used is the radio occultation values.
Yeah, I see. Yeah, just because the TC terminology it gave us the idea of integrated value. So I didn't have in mind that you were like taking the radio occultation profile, which is indeed much better for this work you're doing.
Yes, yeah, it is.
So I think also that we have Andrew. Andrew give a presentation, although we had some challenges with with the at some point we couldn't complete that presentation on that day. But he was actually proposing another kind of method to calculate the plasma sphere in that talk. So I think Andrew could be very interested in this as well. So, well, in my own opinion, I also wanted to see your validation with the TEC. I was looking for that result. Like, are you validating your result with um, the result of the model with the actual TEC at some point?
Yes, that is what this slide is showing.
Okay, let me show you. Let me see.
Yeah. So on the vertical axis on this slide, that's the top. And on the top plot is the GNSS, the TEC from the GNSS. And then on the horizontal, for the first one is the raw cosmic value. And then after we calibrate, you still see my slide?
Yes, I'm seeing, yeah, we are seeing your slide.
Yeah. Yeah, so that this is like the validation using the GNSS TEC. So this is comparing the prediction
Oh,
from
yeah, got it. Okay.
What's the altitude interval for the cosmic TC?
the altitude interval.
Yes.
Yeah, it's for Cosmic 1, it goes up to about 800 kilometers, but for Cosmic 2 is around 500 kilometers.
Above.
So, and yeah, and these altitudes are also part, as you would see, they're also part of the inputs for the model. So the model will learn like when the altitude is high or when it is low also. That was the reason for including, yeah. So if I go back to the inputs, yes, like here, there is the bottom altitude, and also the top altitude. So it says the start of the profile and the top of the profile.
So on the plot you just showed for validation, it gets stuck on 80 EC units. Probably this is the limit for bottom side TC, right? Around 80 and 90. Over
Sorry?
this 80 is maybe the top side contribution. And
Yeah, where
yeah,
where is the 80?
yeah, I'm talking about the left panel. You have these points stuck it in the 90 limit, 90 in the cosmic TC. So
Yes.
compared to GNSS
Oh,
TC,
okay.
so probably this is the lack of top side contribution. Am I right?
Yes, like it's where the values kind of saturate, like where the cosmic values saturate. So like the GNSS TEC grows above that magnitude. So it's not altitude, it's the tech unit. So like 80 at around 80 tech units, the cosmic values rarely go beyond 80 tech units, whereas the GNSS tech units could also still go as high as 140 or 150 kilo tech units.
So the concern here is even with the GNSS receiver TEC, do we actually have that plasma sphere? Because when we calculate that TEC, we consider it a shell layer around 250 to 350, and we don't really account for the plasma sphere. So I think that is where Dr. Andrew comes in. I think he was working on something like that. I'm not sure if I'm
Okay.
right. Yeah.
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 The thing is, except down at the lower TEC ranges, the plasmasphere effect would be smaller than the discrepancies that are shown here between the red and either the blue or the green.
Sorry, Dr. Andrew, I can't hear you clearly.
Hello?
Yes, I can hear you now.
Okay. The plasmasphere content would be small compared to the discrepancies at the higher TEC ranges for the cosmic versus either of the other two.
Yeah. Yeah,
But
that is true.
to the extent that it
And what
incorporates some compensation for the plasmasphere, it must be that the geophysical parameters trigger on the depletion and replenishment in some manner.
Okay, so I think what that Olu was asking or saying is about the thin layer that is normally considered, especially when we're mapping the slant tech to the vertical tech on the GNSS, yeah, for the GNSS data. And yeah, that is only for that purpose of mapping the slant to the vertical tech, and it doesn't mean necessarily that we're looking only at the tech around that. Yes, most of the tech is concentrated in that altitude, which is the reason to choose that altitude, but we're looking at a plane where we can assume concentration of most of the density. But the slant tech already contains signature of the delay that is kind of from the start of the signal at altitude of 20,000 kilometers to ground. So it contains already both plasma sphere and both the plasma sphere and the ionosphere. So it contains electron content from both sides already. That is on the slant tech before we also shift to the vertical tech.
Okay. Sounds good. Yeah. That's relieve some fear. Yeah. Yeah. But you got my point, right? Like
Yes,
we.
yes,
Mhm.
yeah, I did.
Mhm.
I did, and thank you for it. Thank you for the point.
Yeah, sure. Any other question for Daniel?
I think there are some
Oh yeah, sorry, Giorgio. I'm sorry.
yeah,
I'll come back to you. There is a hand that has been raised for a while now. I think it's
okay.
Junior Hill. Do you want to come up with your question, Junior? You can unmute yourself, and then we'll go to Steve.
And there's a question in the chat too.
Oh, okay. Because we need to be on time. Junior, can you ask your question? Why I gather this from the chat? Okay, Steve, can you ask your question, please?
Hello, everyone. Can you hear me?
Yes, we can hear you.
Okay. My question is, so this is like a framework, right? In a way, in a
Sorry,
sense that,
like
in a
what?
sense that, so is this like a framework in a sense that, okay, so I have a cosmic data, and I want to
Yes,
try to see how I can tune it to match exactly or approximately
exactly.
a GNSS data, not like
Yeah.
a prediction model, right?
Yes,
Like,
exactly. Yeah,
oh,
it's more
okay.
like a framework. Yeah, it's more like a
Oh,
framework. Like you have cosmic data and you want
yeah.
to kind of relate it to how much it would be for
It will
GNS
approximate the
equivalent.
GNSS.
Yeah,
Oh, okay.
GNSS. Yeah,
Right. No,
yeah,
that's fine. Thanks.
yeah.
Okay, Giorgio, please go ahead. I'll ask the
There's a
question.
question in the chat. There's a question in the chat.
Okay, so the question in this chart is like saying, why not DST and AP? Why DST and KP? I'm not sure I got that right. Okay,
Okay,
so
why not DST and AP?
I think you show some future analysis and future engineering thing that you decide where which ones are more important to use. So I think that answered the questions. Or if you want to add any other thing, Daniel.
Okay, nothing much, but if he's asking maybe why use AP instead of KP, yeah, then KP is more global opposed to the AP that is more for the high latitudes.
Yeah, and it's 3 hours. I mean, KP also 3 hours. I
Yeah,
think
KP
KP
is
is
also
24
3
hours or
hours.
something. Yeah.
Yeah, it's 3 hours also, but it's more global in
Mm-hmm.
terms of latitude distribution of what happens across both latitudes. The DST is mainly the low latitudes, so the KP also takes care of more latitudinal distribution.
And you also did some visual engineering, right? That gives you what parameter to use.
Yes, yes.
Because this is a model, you can decide to put all of this and then find out which one gives you better results.
Is more significant.
Uh-huh.
Yes.
Awesome.
Yeah, like I showed, the results actually showed that the introducing even the three of them was not that significant.
Mm-hmm.
Yeah, the improvement in introducing both KP, DST, and that were not significant.
Okay. Giorgio, you can ask your
Yeah,
question now.
just my final comment was what I was about to say is that I've read some old textbooks and papers that now these days everybody uses GNSS, but this old technique for the rotation, it doesn't consider very well the plasma sphere electron content because of the magnetic field is weaker. So it relies mostly on the magnetic field effect on the wave of propagation. So I think maybe a good way of trying to get the contribution from the plasma sphere, maybe a comparison between these GNSS receiver and TEC calculation, and further rotation estimation, because you can just try to compare both, maybe remove, subtract the further rotation technique TC to the GNSS one and try to see what's the result.
Okay. Yeah, if I got you clearly, maybe like using an independent different plasmaspheric model. Is that what you said? And yeah, now I'm trying to
Yes, it's
compare.
almost the same, but I was more talking about these old satellites that can use it for further rotation estimation,
Mm,
not the GNSS
okay.
satellite. Of
Okay.
course,
Yeah,
this is
so
something I'm not an expert. I need to
So
check
I
it.
think you guys can continue with the conversation. I think Giorgio will also read your paper so that he has more understanding, and then you are
yeah,
part of the CONGA member now, Daniel. You can always join us.
yeah, sure.
We
Yeah,
bring up
sure.
discussions like this most of the time,
Yeah,
so we will come back to
yeah.
this again. And I will
Okay.
have two more questions, one from Steve and one from the chat here. I think Paul.
Mm.
Obasanjo. Oh, okay, we have Obasanjo in our midst. Okay. He's trying to ask you a question here. What is the
Okay.
significance of the smear parameter?
Oh, okay. Yes, I think the smear parameter is something people also ask a lot. So the smear the smear parameter is the like how many kilometers the profile stretches, because the cosmic profiles are not exactly vertical profiles. So they are kind of slanted somehow. So they stretch across some distance. Like if you take the bottom the bottom point to the top point. So the horizontal spread, the horizontal spread or separation. For a vertical profile, that separation would be zero. But for like a slanted profile, it could increase. So the smear also tells how spread out the profile is and does provide some information for the network to learn how the tech computed from that profile relates with a GNSS station, usually around the middle of that profile. So that's what the smear means, and that is what the significance for the process. That's how significant it is. It also provides some information about how horizontally spread the profile is.
Okay, thank you. We have the last question from Steve.
Yes, sorry, I couldn't ask my question earlier. So my question is, so you used neural networks. So what was the motivation for using a neural network, since this is more like a spatial, modeling approach?
Okay. Yeah. So like we
Or not,
already
why
all
not
know,
use like also try? Did you
yes.
also try maybe like a spatial architecture? Something like
Yeah. So a number of things. First, the volume of the data is huge to try other procedures, and then like to optimize itself. Like if we're doing other procedures, we also have to try to optimize maybe changing functions or changing, depending if we decide also to use polynomials or other functions to change and also to adjust which the neural network does better. So the neural network by itself does the optimization and the adjustment better, and the data is also huge. So neural networks or machine learning in general provide more elegant way to solve this kind of problem.
Okay, awesome.
All
So
right.
thank you very much, Daniel. This is really interesting. One last question I have for you is you mentioned 5 degree, and 5 degree equal to like 500 kilometer, whereby you take the data point for TEC And
Yes.
in this case, there could be a lot of variation between 500 degrees. Is that because of data availability or optimization or
Yeah.
managing things to make sure that you don't miss too much data?
Okay. Yeah, we think 5 degrees provide a kind of in between, not too small, not too large value, and it's seen in a lot of other papers too that do similar kind of co-location of space and ground measurement. So, yeah, you are right that if we take a smaller value, like a smaller radius around the station, then we would get better agreements because 5 degrees. This is actually in another study. We are trying to look at how much this varies, like maybe from 1 degree to 2 degree, 3 degree. How
Yes, that
much
would be awesome. That would be awesome. Yeah.
the variation is.
Yeah, because
So
if you have
that is true.
some ionospheric things going on at, well,
Some distance. Yeah,
yeah,
you're right.
yeah, you could do that study so that you know the feeling, you have some feeling about what 5 degree means. So that will give
Yes.
more concrete knowledge on this.
Yeah.
Anyway, thank you
That's true.
so much. This is really, really, really educational, and we enjoy every bit of it. The internet wanted
Thank
to
you.
give us some concern, but we overcome it.
Yeah, sorry about that.
Yeah,
Thank
thank
you.
you again very much for your time and for preparing
Yeah.
this presentation for us. We appreciate it a lot. And
Thank you. I also appreciate the opportunity to share our work.
thank you. You can stop sharing now, and I think we are coming to the end of today's meeting. In the next meeting, we have so many people or couple of people that we are considering, so we cannot really determine or say emphatically right now that we have a presenter. So I'm going to let us know in the email who will be our presenter for next meeting. So I think if we don't have any other thing, Yinka, do you have anything to add? Giorgio, do you have anything to add? We need to round this up.
No, just to thank again Daniel to be here with us.
Yeah, thank you so much, Yenka. Nice always meeting you. Yeah.
All right, guys. Thank you all. Thank you all for your time, and we will see you next week.
Hello, Doc.
I mean, next
Sorry,
month.
I joined late.
Oh, okay. You want to ask something?
Hello, can you hear me?
Yes, we can hear you.
Yeah, sorry, I joined late. I was so busy, but I'll try to make it the next edition.
Yes, please.
Yeah.
We'll see you on the next edition. That will be 23rd edition of CONGA, and we will see you then.
Okay.
Yeah. So
Thank
thank you everybody. See you
Yeah.
next month. Thank you.
Thank you, everybody.